Okay, let us begin. All right, last time we spoke about related rates. Today it's going to be a completely different topic. One that might seem long overdue. Because we're going to talk about linear approximation. Which was the whole point of a tangent line, you might recall. Us being able to approximate a function by a straight line, and hence talk about the slope of that function at some point, was the whole reason why we decided to invent the derivative. So we're going to go back to that, back to our roots for a little bit, talk about something called linear approximation, and the idea of a differential, which is just another perspective on linear approximation. That's what we're going to talk about. So the idea here is that this is the process of approximating function f of x close to a point using its tangent line. At that point. The idea being, sometimes you'll have functions and they're really very complicated to deal with. And so what we do is, if we want to talk about the function at a certain point, at some location where it's just very difficult to deal with that function, and even more, we want to talk about the rate of change of this function at that point. What is the slope? How fast are things changing? But the function itself is kind of troublesome to deal with. What we can do is go to a point close to that point where we actually know a lot of information about the function, draw a tangent line, and then we can use that tangent line, the equation of the tangent line, to approximate the equation of the function. So basically the idea is kind of this. So here's a function doing as it do. Let's say we're interested in this point. We want to know what's going on at that point. But the function is very complicated at that point. Or it might not even exist at that point. Maybe you actually want to predict the future somehow. And you know about all past events before this point, and you kind of want to know what's going to happen a little bit ahead. And so, let's say at this point, we know a lot of information. So we, at the point A comma f of A, we have the information, right? And we kind of know how to deal with the function at that point. And on top of that, we also know how to create a tangent line at that point. So while the function might be very complicated to figure out how it's behaving over here, we can definitely know how its tangent line is behaving, right? And that will actually give us an approximation. And what we're going to do is we're pretty much going to use the coordinate on the tangent line, right above that guy. So we'll use the green point to approximate what's going on at the point x comma y, and we will know exactly what's going on at that green point because it just comes from the equation of a line, which is super simple. It's easy to deal with. Right? And the process of doing that, using the green point to approximate what's going on at that point, that is called linear approximation, because we're using a straight line to approximate something, so we're using a linear method of approximating something. Now, as you can see, the closer we are to the point of tangency, the smaller the difference between these two are, right? So it's not something that you'd really apply if it's like way down the road. You really want to apply it close to a point where you have all that information. And sometimes that's all you need. So I know a few of you are also in the, one way this can apply, I know a few of you are also in the business schools. Technically you shouldn't be here, but you want to be here, and that's fine. One way in which you might see this is in something like high frequency trading. So basically, you can definitely track a market, track a stock, you know what it's doing. What if you want to know what it's going to be doing tomorrow? What will it be doing 5 seconds from now? A human being can't do a lot in 5 seconds. If you have a supercomputer selling and buying stocks, you can do literally millions of transactions in 5 seconds, right? Now 5 seconds is nothing, right? For a stock to move one blip in 5 seconds, you're not really going to know much difference. However, even if that difference is like a few cents on the dollar, right? It drops by a few cents. If you can have a supercomputer figure out that that's kind of where the stock is heading 5 seconds early, it can literally make millions of transactions within those 5 seconds. And those few cents adds up when you're making a few cents millions of times, right? So you can even use this kind of thing to kind of predict what's going on in the future, because things shouldn't change that rapidly. Very few things actually change like drastically in a very short period of time, right? If you have the machinery, knowing what's happening just a little bit in the future can be all you need to really rake it in. Anyway, that's kind of the idea. We know what's going on somewhere. We kind of want to know, approximate what's going to go on somewhere else a little bit off to the future. Just a little bit of distance away. Figure out what's going on. How is this function going to be behaving? So let's do some notation here. So that is, here we have some differences here. So here we know what the y value was. We've moved to a new y value that we'd like to know what that is. The difference between these two, the notation for that we call delta y, or the change in y. Now, there's also the notion of the difference between that y value and the y value from the tangent line itself. Distance between that we call dy. And you can even interpret that dy as literally the numerator of the Leibniz notation of the derivative, which is one reason why it's convenient. So dy is sometimes used to approximate the delta y. The closer these points are to the original point, the closer these values will become. So we can approximate the change in a function, the change in the output of a function, by approximating the change in its tangent line from that point. Okay. So this is called delta y, that's uppercase delta. This is supposed to be like a lowercase delta, but we use the English letter d because whenever we use lowercase delta, it actually means something else. It's a very special derivative that you'd see in Calc 3. But that's kind of the idea. You kind of use this guy to approximate that guy, so I can know how the function is changing by looking at how the tangent line is changed. And if we're super close to the original point, the difference won't be that much. And sometimes just being off by a little bit is okay. So that's kind of the overall idea. So the idea here is the y of the function close to a is going to be approximately equal to the y for the tangent line close to a. In fact, that's kind of the idea that we use to develop a tangent line. In other words, to figure out what is going on in f of x, I need to figure out, one way to do that is to figure out what the tangent line is. Now you might want to know, how would we find the tangent line? Remember, a tangent line is just a straight line. So the tangent line has the form y minus y1 equals mx minus x1. And we know what makes something a tangent line is that our m is the derivative evaluated at the point. So I can kind of, this is our original point, f of a. Move this to the other side. So the y for the tangent is actually f of a plus f prime of a times x minus the original x f of a. And so we can actually plug that in here. So our function output at x is going to be approximately equal to this expression. So we can use this expression to approximate what our function is doing, and it's the equation of the tangent line at a point close to that guy. And this is called the linear approximation formula. Right? It's what we use to approximate a function via its tangent line. The right side of this expression, we also give it a name. We call this the linearization of the function. Sometimes called uppercase L of x. It will be f of a plus f prime of a times x minus a. So that's called the linearization. It's pretty much the right side of the linear approximation formula. So if I have a function and I ask you, find the linearization of this function at this point, you are simply going to compute that expression. Now let's actually try this. Now we are in Calculus 1, so there is no function that we're going to look at which is terribly complicated in the real world sense. I'm going to illustrate the ideas to you by using simple functions that you kind of know what they're about, you kind of know how to deal with them anyway, but we're going to deal with them via this formula for you to see, oh, it's not really much difference between the function and this guy. So let's actually do some examples here. Again, if you see a problem about this kind of thing, linear approximation or linearization, the statement of the problem is going to be very similar to this. It's going to say something like, use linear approximation or differentials. We'll talk about differentials later. It's pretty much the same thing as linear approximation, except you think of it from a different angle and you use different notation. But it's pretty much going to be the same thing. Use linear approximation to estimate or approximate, and they'll tell you some value. Let's say we want to use it to approximate the square root of 3.99. Now, not a particularly complicated thing to figure out, of course, but I just want to show you kind of how this would look. So here's something you want to figure out what this guy is. At least you want to approximate it without a calculator, probably. Or even if you had a calculator, sometimes you might still need to do this. So the first thing you might do is try to set up maybe a function that you think can actually track what this value is going to be. Now if we want to find the square root of 3.99, what would you think a nice function to use would be here? Yes?
The square root of x.
Square root of x, right? If I think of the function square root of x, to find square root of 3.99, I can simply think of that as evaluate the function square root of x at the point where x equals 3.99. So that's what we would do. So you're going to be given a description of something that you want to compute, and step one is you're going to set up a function. So what I would do here is I would set f of x equals the square root of x. You can immediately start to note several things. You can reinterpret the problem statement in terms of this function. You can note we want f evaluated at the point 3.99. We also can say that that's the x value that we care about, 3.99, but that's not terribly convenient because who knows the square root of 3.99 off the top of their head. Can you think of a number super close to 3.99 where you do know? Yeah? 4, right? Everyone knows the square root of 4, okay? That's easy. Now, there are many numbers for which you know the square root. You know the square root of 9, 16, 36, you know the square root of 1. However, remember the idea is for this to work, you need to be super close. So you really want to pick the closest value to 3.99 that you can, that can approximate it. So this is the closest thing to that, and it's relatively close. It's only off by 2 decimal places. It's the closest thing to that that I know of, and I know an easy way to deal with the function. So, in other words, x is the ugly value. I mean, no numbers are ugly, you know what I mean. You don't know how to deal with a in our formula is going to be the nice value. For it to work, it must be close to x, as close as you can get, for which we know. And the idea is we need to be able to develop the tangent line here. So we should be able to know what is the function's value at a and what is its derivative at a. So that's the idea. Pick a nice number close to the value that you actually care about. Right, so we care about here, but we don't really know what's going on there. Let's pick somewhere close to that, and let's create a tangent line at that nice point. Right? And so, knowing that I need to be able to evaluate these, I should probably find the derivative. So to differentiate the function, let's just say find f prime. So here, your f prime of x would be equal to what? What is f prime?
Negative.
1 over 2 radical x. Right? You can think of that as x to the half, do the power rule, you get 1/2 x to the minus a half, which is 1 over 2 radical x. First time we derived it in that form. So we find the derivative. Now you're going to 3 find the pieces. Find f of a and f prime of a. So here, our a was 4, so I'm just going to plug in 4 into this function. That's the square root of 4, so that's 2. F prime of a, well that's just f prime of 4, and plug that in, 1 over 2 radical 4, that's a quarter. 4. Use the linear approximation formula. So here we can say that the square root of 3.99, that's the thing I care about. This is actually just f of 3.99, but that is approximately equal to, by the linear approximation formula, to be f of 4 plus f prime of 4 plus 3.99 minus 4. So this is me going into the linear approximation formula that tells me f of x is approximately equal to f of a plus f prime of a times x minus a. So I simply go to the linear approximation formula, I plug in all my x's and my a's everywhere. Everywhere I see an x, plug in 3.99. Everywhere I see an a, plug in 4. So this is going to be 2 plus a quarter times minus 0.01. And that is 2 minus 1 over 400. 2 is 800 over 400, so this becomes 799 over 400. And that's my approximation. So the square root of 3.99 should be something close to 799 over 400. Now just for fun, let's actually compare. So if we look at 799 over 400, tell me roughly what is that? So, versus the square root of 3.99. So these are calculators or something. 799 divided by 400, tell me roughly what is that?
It's roughly 1.9975.
1.9975. It didn't tell you anything else? Okay. Actually put this in. So use the square root function in your calculator. Square root of 3.99.
It's very close.
Well, what is it?
It's 1.99749. It's not there.
Well, look at that. No calculator, didn't put my hands, nothing up my sleeve, no magic tricks. And I was correct up to, with rounding, 4 decimal places. That's me. I'm just one man. I'm just Javon. Imagine if you gave a supercomputer this kind of strategy. Yeah, this is kind of complicated. All the human beings are out there running around trying to figure out what's going on. Here, use this. Compute that, do that a million times in the next 2 seconds. Have the humans on their feet. Yeah. So you, look at that. Just by hand, we are good up to 4 decimal places if we round it. Nice, that's the power of this formula. Now, square root function isn't a particularly complicated function, but this is just to illustrate to you the power of this method. Let's actually do it again. Just to get you used to actually using this. Let's approximate a cube root. Let's say I ask you to approximate the cube root of 8.01. And again, the problem might be phrased something like, use linear approximation to estimate the cube root of 8.01, or something like that, something similar. So what would be the appropriate function here, do you think? Cube root of x seems to be like a nice candidate. And so now what I would do, find this derivative, because I know ultimately I'm going to need it eventually. So this is x to the 1/3. The derivative is 1/3 x to the minus 2/3. So that's going to be the derivative. And we can also note here we have our x value is 8.01. That's the ugly value that we want to figure out what's going on. The a value is a nice value that's close to that we kind of already know what's going on, which is 8. 8 is pretty close to 8.01, and I actually know the cube root of 8. So now, let's actually find those values. 3. So f of 8 is the cube root of 8, which is going to be 2. F prime of 8 is going to be 1/3 times the cube root of 8 squared. How do you find that? What's that going to be? 1/12. How did you find that?
8 squared would be 64, and the cube root of 64 would be 4.
I probably wouldn't have done the square first. That is kind of what I wanted to see. Remember, you kind of have the option of switching them, right? So if you have x to the 2/3, or or something similar. Notice that because of multiplication, you can think of this as x squared to the 1/3, or you can think of that as x to the 1/3 times squared to the square, right? Now, if your base is positive, it doesn't matter the order. So I'd probably take the cube root first. Cube root of 8 is 2, then squared, you get 4. 4 times 3 is 12. A lot nicer, you can do it in your head than you don't want to get with bigger numbers if you don't have to. So okay, I want to approximate this. That seems like a nice function to use. The choiceless function doesn't have to be that great, by the way, but in this case, it seems to be the obvious choice. Realize that what we want is to evaluate this function at that point, and we know what's going on at that point, so we find these two calculations, and then we use the linear approximation formula. So for the cube root of 8.01, we know that is f of 8.01. That is approximately equal to, by our linear approximation formula, that guy. This we know is 2. That we know is 1/12. This we see is 0.01. That's 2 plus 1/1200. 2 is 2400 over 1200. This is 2401/1200. That would be my guess as to what this thing is. Let's see how good of a guesser I am. So compare this number to the actual value. It's going to be 2 something.
2.0008 and then 3.
Okay. Plug this in.
That one's 2.00832986.
Look at that. If I just round it here, 6 decimal places, not bad. So, if you're ever on a deserted island, no calculators anywhere, and as a matter of life and death, you need to figure this out close to 6 decimal places, now you know how to do it. See, that's math applied in the real world. I want to see you compute the cube root. It could be your pickup line. You're gonna be like, oh my god, you're so smart. Fantasies. Okay, yeah, so we can actually approximate things pretty well, right? Again, not a very complicated function, but I just wanted to illustrate the point to you that we can kind of guess. We know what's going on at the value of 8, but if we just move a little bit over, we can guess what that value is going to be, and we can be pretty right. The closer we are to 8, the better the approximation is going to be. I mean, even if we went to like 8.001, we'd get even better. We'll probably get a few more decimal places out of this. So the closer you are, the better the approximation gets. So that's pretty cool, I think. So this is just for illustration purposes. Of course, the cube root function isn't totally complicated. You just calculate that whenever you need to. But it's nice to know if the function was complicated and if you could actually find the tangent line, which a lot of the times a computer can get that for you by just plotting point by point. You can actually have some predictive power or figure out what's going to be going on close to the point of interest. Here's another example. Sometimes the problem can be phrased in asking you to find the linearization of something and then using that later to do something else. So here is a problem. Find the linearization of of x equals sine of x, the sine function, at x equals pi over 6. Let's see. So remember, the linearization is literally just the equation of the tangent line. That's what it is. I mean, we call it big L, but it's the same thing. So recall, I mean, we just did it a few minutes ago, but the linearization is the function big L, which is equal to what? General formula. Yeah.
F of A plus F derivative of A
Evaluated A, yeah.
multiplied with x minus x.
That's the linearization formula. And here, our A is what is the A here?
Cos pi by 6.
Pi over 6. So that's the given value. So this is the linearization at A. So if we want the linearization at this, it means that x value is the A value. Right? We're fixing that value at A. So we're simply going to plug that in. So here we know f of x is sine of x. By now we know that the derivative is the cosine of x. So this means f of pi over 6 is going to be sine of pi over 6, and f prime of pi over 6 is going to be cosine of pi over 6. Sine of pi over 6 is sine of pi over 6. Yeah? It's a half. Cosine of pi over 6.
That's not right here.
You guys should know that. Okay, so now we can say the linearization is going to be f of A, which is this guy, is going to be a half, plus f prime of A, radical 3 over 2, times x minus A, so it's x minus pi over 6. You'll notice that this is the equation of a straight line. That's your slope, and that's your x. If you multiply this out and then add it to the half, that will give you the y-intercept. And that's the linearization of sine. Now sine is one of those functions where it borders on the simple and the complicated. Like, yeah, we all kind of know what sine is, what it is at certain values, how to graph it. Hopefully we know all that. But if you ask a random person, okay, what's the sign of this? It's not really a nice definition where you can just plug in and calculate something there. Right, so what is sine of 2.73? Like, I don't know. What do you plug in to get that? Right, it's kind of complicated, even though it's something that's very familiar. But if I ask you to plug in a value close to pi over 6, you can instead use this equation to figure that out. You literally just plug that value here and calculate it. So you can do this a linear approximation. That's the linearization of this guy. So close to the value of, when x is close to pi over 6, your sine function behaves like this tangent line. So sine looks like that. Pi over 6 is, this will be at pi over 2. So pi over 6 is somewhere here. So over there, we have this tangent line. So the actual value here is a half. But if you're a little bit to the left or right of that, and you want to figure out what is the sine function doing, you can literally plug that value into the tangent line instead, and it'll give you a pretty good idea. Let's talk about differentials. Similar idea here. if your y is equal to f of x, notice that you can find the derivative. You will get dy dx equals prime of x. In other words, you can say dy is equal to f prime of x dx. And whenever we kind of break up the Leibniz notation and we think of the derivatives and the dy and the dx as separate entities, these guys, we call them differentials. This is called the differential of y. And this guy would be called the differential of x. Now remember that your differential of y is really approximating delta y, right? So this is an approximation for delta y. And by the same idea, the differential of x is an approximation for delta x, but it turns out that that's actually going to be equal to delta x. Because the input values, we know what's going on. Someone's giving you the x value. You know exactly what the change in the x value is. So the approximation here is pretty much spot on. It's the y value that we don't know what's doing. Right? So if you look at that previous graph I gave you with the tangent line, the y value I didn't know, but of course the x value, the change in x, the approximation for that, I know exactly what that is. There's no approximation. The x values are exactly the same because they're the inputs. It's the y values that we're not sure. Well, how is the y going to respond if I change the x by this? So in other words, you can essentially write this guy as x minus a, right? So again, you have the derivative times the difference in x values. So the idea here is the new y value is going to be the old y value plus some change that we're approximating by delta y, right? So it's like, if we want to figure out what's going on at f of x, which is the new y value, figure out what's going on at the old y value, which is going to be f of a, is the point that I know, plus dy, which I know dy is equal to this. That's just f prime of a times dx. Well, that's just right? So you cannot kind of translate across them, right? But a lot of times the idea is when you're using differentials, you're kind of thinking in this mode. You're kind of thinking as an old one plus a delta y where I'm approximating that by a derivative. Whereas the linearization really fleshes this out into a very plug-and-chug formula that kind of shows you everything that you need to plug in. Yeah?
What do you mean by old y?
The old y is the guy that we already know about. Right? So when I was here, so here at a, I know what f of a is. That's the old y. I know, that's the guy I already know. The old news, right? But then if you shift off a little bit, now I don't know what's going on because the function is complicated. This is the new y that I'm trying to find. So old y in the sense that it's old news, we already know about it. We fully understand what's going on over there. We want to figure out what's going on at this new point. You can do it, think of it in this form. If you think of it in this form, this part here is called a differential. But really, if you translate everything, it's exactly the same as the linear approximation. For some reason, people like to use the differentials idea when dealing with more word problem kind of things. So we don't have time to do this example, but I'm going to write it down. Maybe you can try to see how to apply what we know to solving it. But a problem like this will typically be solved using differentials because it's just kind of nicer to write up. So here is a problem that we will complete next time. Maybe start thinking about how you would do it.
we could call that. I'm final exam session, quick call.
Relative error means to state the error in terms of a percentage of the actual value. So you can say, oh, we're off by 2%, relatively speaking, or something like that. But here's a kind of problem, again, where something like differentials or linear approximation would be used to achieve. Let's say you have some object that you go out, you take measurements, and you find out about that object. But maybe the machinery you're using isn't completely accurate. It can be off by some error that you can know how much off it can be. So yeah, the machine tells you it's 20 centimeters, but it could be off. It could actually be 20.01 centimeters, or maybe 19.99 centimeters, right? You can be off by that much. There's an error, right? So now the thing is, if you want to use these values in future calculations, like if you're calculating volume, how does an error over here affect the error over there, right? And that's something that you can use linear approximation to figure out. Right? So try to figure that out, and problems like this come up in engineering all the time. And it's just a matter of, is the maximum possible error something that we can let go, you know? So do we really have to be accurate in the amount of cement we're using on this 1 mile bridge? Oh well, yeah, if we're off by too much, that's people's lives lost, you know? So that's a problem that you'd want to figure out. Anyway, you can try that. I'll see you guys on Tuesday.